Okay, so last time we just kind of barely started talking about Gauss's divergence. We hadn't even gotten to the actual theorem yet, but we were building it up. And so let me remind you the big picture. A lot of the theorems that we're talking about here are structurally the same. It's the same ideas over and over again, right? So real broad strokes, we have to set up a convention for what we mean by boundary orientations. We're going to need to identify what is the appropriate accumulating quantity. When you're doing the fundamental theorem of calculus, it's change. When you're doing Green's theorem, it's circulation. Right? When you're doing the 2D divergence theorem, it's boundary flux. Right? It's different for every theorem. Once we realize we have an accumulating quantity, we observe that it behaves like stuff, and once you know it behaves like stuff, we can talk about the corresponding density, and once you have a density, then you can just put it all together, just like we have every other boundary theorem that we've talked about, what I sometimes call boundary theorems. I sometimes call them accumulation theorems. Anyway. Okay, so now let's remind ourselves of all these details. This is where we ended last time. I talked about the convention for how to talk about the boundary of a solid three-dimensional region. So here's a three-dimensional region. If you talk about its boundary surface, which of course has two chunks, right? Boundary comes with now an orientation. Now I have to tell you what I mean by what is the orientation that is assumed and implicit in that word. Again, whenever you see the word boundary in chapter 6 and 7 context, that means oriented according to convention, and the convention is away from the solid. Right? The boundary is always the kind of the border between solid and not solid. Right? So the orientation is away from the solid and into the not solid. Right? Okay. Notice sometimes that's inward. It's a sloppy convenience that usually is right, but usually means not always. To say that it's always outward. It's not technically quite always outward. It's always away from the solid. I believe that's where we ended last time. So what is the accumulating quantity that we'll be dealing with? And it is boundary flux. Boundary flux, as we're going to see in just a second, accumulates. And to be more precise, it accumulates over solids. So, boundary flux accumulates over solids. What I mean by over solids is that it's the solid on the inside here that if you break it into half and compute the boundary flux at one side, the boundary flux at the other side, and add them up, then you get the boundary flux of the whole. The thing that you break up into pieces is the solid, not the surface. So, okay, well let's confirm that this works. So, looking at the left half over here, the boundary consists of this piece, which is oriented that way, and this piece, which is oriented that way, away from the solitude boundary we're talking about. R1 being the solid we're talking about, away from the solid is like so. Okay, and then we look at the second half. The second half of the solid right there. What can I say about the boundary of that second half? Well, there's this piece oriented away from the solid, of course. And then there's this piece oriented away from the solid. Again, we're talking about the boundary of R2 here. And so away from R2 would mean that way. Okay, so now that we've got on the page here the boundary of R1 and the boundary of R2, I just need to know, do those add up to the boundary of the whole the whole lump, right? And the key point is, as you can probably guess, that this face that I'm trying to highlight there in red, that face appears twice in this summation of fluxes, right? So it appears oriented to the right as part of the boundary of R1. It appears oriented to the left as part of the boundary of R2. And so when you add those up, given their opposite orientations, all that stuff in the middle cancels. Right? So those two terms, this face oriented to the right, this same face oriented to the left, those fluxes cancel, thus leaving us with, as we hoped, the boundary flux for the solid. So boundary flux does indeed accumulate. Everybody buy it? All right. Okay, this is tremendously valuable. Knowing that something is an accumulating quantity means that it behaves like a stuff. We've talked about this in the context of different kinds of accumulating quantities. But the big idea is, if you have some accumulating quantity that is defined for the whole, and you want to know how much of that is in, let's say, this little box. Let's see, well, I guess I'll use green. How much of the accumulating quantity for the whole is in this little green box? No problem. I can just take this whole solid. I can chop this whole solid up into chunks. Right? And I can compute how much of the accumulating quantity is in each one of these little boxes. And how much of the whole is the sum of the parts, so whether I think of the accumulating quantity for the whole or whether I think of the individual little boxes and the accumulating quantity for each one of those, it's still the same thing. And so how much is in this box? Well, whatever I got for looking at the accumulating quantity for this box, that's how much is in there. Just like with mass. And that's how mass behaves. Mass has a location, right? So I make the case here that any quantity that is intrinsically an accumulating quantity over solids has a location like mass, and therefore it behaves like stuff. I like the word stuff because it's sort of non-specific, but it still conjures that it's a concrete physical thing. Right? Now, obviously, boundary flux is not a concrete physical thing, but it acts like it, so we're going to pretend that it is. And that's a very nice convenience that when something acts in a certain way, you can treat it in that certain way and nothing will go wrong. So one thing you can do with stuff is you can talk about densities. And so reminder, we can talk about what we call, I guess in high school they just call it density. I'm going to call it here mass density because the big idea is you're looking at how much mass there is, thus the term mass density. How much mass there is per unit volume, right? And mass per unit volume is what we know as density. Again, I like to clarify that the accumulating quantity is mass, so we call it mass density. Copycatting, as we do, we're going to use the term flux density to talk about what we have when it's not mass but flux for a given region that we're interested in per unit volume. And because the accumulating quantity in question is flux, we call this now flux density. And we can make this case at all because, as discussed above, because this is an accumulating quantity, flux actually has a location. I can talk about how much of the outward-oriented boundary flux there is on this individual little region. Okay, is everybody happy? Okay, so good deal. We are in business. Now, let's see, let me clean up my mess here. And we have this idea of flux density, flux per unit volume. I'm going to wave my hands and skip the details of tedium that are necessary to get down to this formula right here, and it's not that bad, but it would take a bunch of time, and I don't think it's a good investment of time. It's just details. 10 years from now, you would not remember those details, but I think it's essential. It's critical that you do remember what the point of this expression is. It's where it comes from in the actual algebra, not the point. The point is that it represents flux per unit volume, accumulating quantity per unit size, where specifically flux is our accumulating quantity. That's what's really important. That's the big takeaway. And y'all will recognize this as something we saw in Chapter 3 called divergence, for which we have these two different notations, both very common. This is what you're going to see, what the formula for it is, and this is why we care about it. Everybody all right? Now, before we put it all together and write down our big theorem, I do want to remind you that these flux densities have a second purpose, right? And you may recall we were talking at some point about the fundamental theorem of calculus. It seemed silly at the time, but change is an accumulating quantity. And the derivative kind of tells you where the change is happening, right? When the derivative is large, that's literally where the function is changing, right? The function there's a lot of change per unit size. Slope is literally telling you change per unit size. The derivative is literally change density, right? So not only is that density the integrand for a theorem, that density points to where the accumulating quantity is, by where is it biggest. Right? If the slope is steep, there's a lot of change happening there. If the slope is not steep, then there's not much change happening there. Right? So I want to point out the same applies here with three-dimensional divergence. And thus this example right here, here I have a vector field through which, or of which there's a certain amount of flux through a certain ball that we don't actually care about the details of the ball. But the point is there's going to be some amount of flux. Where is that flux actually happening? Again, don't make the mistake of thinking that it comes from where it's calculated. That's not really how that works, right? The flux comes from the interior, I claim, and the divergence points to specifically where. So divergence, that we can easily compute, that's what you plug into with your 2 points, A and B. So you plug in those 2 points, see where the divergence is biggest. The divergence is biggest here, so more flux is coming from B than is coming from A. Just like if the derivative is larger, that means there's more change coming from that point than the other. Everybody all right? Okay, so that said, here's the big theorem, putting it all together. I'll zoom in a little bit. First observation, flux. On the one hand, flux is a weird formula that we can write down, that we can compute with various expressions that we've already developed, I suppose. Right? But I don't want to think of it as an expression. I want to think of it as a quantity. I want to think of it as by itself, an object of intrinsic interest. Okay. Second observation. It's an accumulating quantity. Whole's the sum of the parts, which is literally what this equation says. The whole flux is the sum of the little pieces of flux that you get when you cut it up into pieces. So the whole is the sum of the parts. And of course, then the density argument comes up, because any little piece of the accumulating quantity is density times size. And so density, as we discussed above, is what goes here. And the density is divergence, as previously discussed. Again, I skipped the algebra and the details on that, but that's the big takeaway, is that divergence is that density. And so having taken these three kind of, if you will, separate observations, putting them together like this, then what we have is a new theorem that says that if you want to compute a boundary flux, one thing you can do instead to compute that is to just take a triple integral over the interior of the divergence of the vector field. Everybody happy? All right, so this is called Gauss's divergence theorem. Okay, now there is a big asterisk on this. This is an important asterisk, and I'm going to come back and dwell on this asterisk in a few minutes, but I'm going to say it emphatically first, just so we all know what I'm talking about here. This is the big asterisk right there. Gauss's divergence theorem does not tell you that for any flux you could just compute this triple integral. No. Very importantly, no. Gauss's divergence theorem only computes boundary fluxes. Very importantly, boundary fluxes. In fact, if you look back at the argument that we made, all this business about accumulating quantities and all that, right? What makes this accumulation happen? Well, we're looking at the boundary of the object on the left, the boundary of the object on the right, and the boundary of the whole. Boundary is intrinsic to the argument we made, and therefore a strict condition on our theorem here. Is that cool? Everybody happy about that? Okay, so let's see an example. All right. Inward-oriented unit sphere, vector field given, compute the flux. If you look at the statement of the question here, notice, well, first thing you notice it doesn't say use Gauss's divergence theorem anywhere in the statement of the question, right? So all it says is compute the flux, and you can compute that flux by whatever means, I suppose, but you don't want to choose a tool that isn't good for this problem, right? If you were to parameterize this sphere and plug and chug, you'd have a nightmare on your hands. Absolute nightmare. Remember, when you parameterize the unit sphere, you're probably going to use the spherical graph parameterization, which is chock full of trig, which means this vector field is going to be a nightmare of trig. You don't want to do that. Okay, so how are we going to do this? Well, we have a question about flux. We have a brand new shiny theorem about flux. Kind of seems like we probably want to use the new theorem to compute the answer to the question. But again, our theorem comes with an asterisk. It is only for boundaries that this theorem applies. So this surface that I was given, inward-oriented unit sphere, is that a boundary? I ask rhetorically. Looking at our surface here it is. Unit sphere oriented inward. Is that what a boundary means? And tragically, no, it isn't. So, bummer, right? Does everybody see why I'm unhappy about that? Our theorem's very strict. This doesn't fit. Dead in the water. Okay. All right. Now, good news. So let me put an X through that. So this is not a boundary. But there is a very similar surface, and now the way I've drawn this is going to get confusing. So I'm going to redraw. I'm going to draw my S surface as I'm just going to draw just kind of the left part. I still do mean the whole sphere, but I don't want to trample my own color coding, right? So this whole sphere, oriented inward, that's our domain. Not a boundary, but it's not that far off. After all, there's the same underlying surface, the same sphere, ignoring orientations, but oriented outward is a boundary. Is that cool? Everybody comfortable with that? So really, orientation was our only problem. The sphere, outward oriented, is a boundary. So what we're going to do, and this is just like the first example we did with Green's theorem a ways back, we're going to observe that the flux I've been asked about and the flux that would be so much easier to compute because this surface in blue is a boundary, those two surfaces differ only in the orientation and you can deal with orientations with a minus sign. Everybody good? So the green surface is what we are obligated to care about because that's what the question was asking. I have now related it by way of this orientation observation and this minus sign. I've related what I need to something that I have tools that I can work with. This S minus, being as it is a boundary, I can come up here to the divergence theorem and say, aha, that S minus, that is a boundary, and therefore I can write the divergence theorem. So the whole rest of this calculation down here is just to observe, here we go, that S minus is the boundary. Boundary fluxes are triple integrals of divergence. That's where the divergence theorem, Gauss's divergence theorem, kicks in right here. And now I've just got a triple integral to plug and chug. Cool. Is everybody good? All right. Okay, now, there is a little bit of a trick about computing this integral, and I'm going to try to point out what that is. After all, let's see here. I need to compute the divergence. Divergence ends up being 3 plus x. By the way, make sure you're good with computing the divergence. Our vector field here, you've got to apply the usual divergence formula, and the divergence formula says I'm going to take the x partial of the first coordinate, that gives me 3, then the y partial of this second coordinate, that gives me x, and then the z partial of this third coordinate, which of course just gives me 0. I can ignore that. And so my divergence is 3 plus x. That's just details. Make sure you're good with that. And now how do I compute this integral? The domain's a ball. I really like balls because they're symmetric. There are lots of symmetries. Tons of symmetries to choose from. Tragically, this function is not odd through any of those symmetries. It's also not a constant, so I can't make hand-wavy geometric arguments. The beautiful idea here, though, is to rewrite this one integral into two separate integrals. Each one of which is conveniently susceptible to an easy argument. Integral of a constant is just it's going to be 3 times the volume. High school geometry formulas for the volume of the sphere. Integral of x over the unit ball centered at the origin, symmetry argument. Right, details for y'all to plug in. And so nice and easy answer results. Yeah.
For the symmetry argument, what would be the plane of symmetry?
Yeah, right. So I need, first of all, I need my plane to be a symmetry of the ball centered at the origin, and so any plane centered through any plane that contains the origin will satisfy that part. But I also need x to be odd. And now let me try to reverse engineer what the plane ought to be. If I want x to be odd, I'm looking for a reflection where the x coordinate turns into negative x. And now can I think of a plane, a geometric plane, where x goes to minus x and reflection through the yz plane? We'll do that. So yeah, I think the yz plane is, in fact, your only option. There, yeah. Is that cool?
Yeah.
Everybody else all right? All right. Okay, now before I get into the physics examples, I do want to give you all a warning. This is a nasty landmine that I always see students step on, and it's brutal. Like I say, I've already kind of told you the relevant detail. It's about the fact that Gauss's divergence theorem only applies to boundaries. This is not a minor point. This is a huge point, right? It just doesn't make any sense at all. It's complete garbage, symbolic nonsense. If you try to apply Gauss's divergence theorem, then the surface isn't a boundary. And here's how it happens. Here's how students step on this landmine. I'm going to presume that we have a question, which is, compute a flux through some surface. I'm going to call it P, just so it doesn't look like S. Compute the flux through some surface P, some vector field dot ds. And now some secret information that I'm going to write down, just so we'll know what the nature of the problem is. I don't want to bring a bunch of algebra into it, though. P is not boundary, and secondly, the divergence of F is 0. Let's just say, and again, this kind of thing happens actually more often than you would think, where you've been asked to compute a flux over some non-boundary surface, and the divergence ends up being 0. By the way, there is a really cool thing that happens when the divergence is 0. We'll be talking about that later, probably Monday of next week, if I had to guess. But see how it plays out. But when the divergence is 0, there's a really neat trick. There's a powerful tool that we can invoke. More on that to come later. What are we going to do in this case? We've got a flux to compute, and what students will do is, to this question, they will say, okay, well, we're looking for flux F dot ds. Now, the students already kind of committed a little crime here, but come on, we've all done it. Leave off the domain, when, of course, I understood. It says right there what the domain is. Why do I need to write it down every time? That's understandable. But then students look at this and they say, okay, well, flux. Well, hey, this is a flux, and apparently fluxes are triple integrals of divergence. And so the student will see this, again, being sloppy about the domain. And then they'll say, oh, well, that's a triple integral of 0. And then they get 0 and, walk away feeling confident. Right? Tempting? You can see the temptation. There's a strong allure to writing this down. This is worth practically nothing. This is all. This might be worth 2 or 3 points out of 20. So let me explain why. So first of all, the student is applying a theorem that does not apply. Right? Gauss's divergence theorem does not apply. Gauss's divergence theorem requires that this be a boundary, which this, in fact, isn't. So you can't invoke Gauss's divergence theorem. It does not apply. Well, that's the first big problem, right? But I want to emphasize how much it doesn't apply. This is not a formality about differentiability or something like that. It doesn't apply because it's not just that we need this to be a boundary for sort of abstract purposes. I need it to be a boundary of something, because that something is the domain for my triple integral. So if your flux that you're interested in, if the domain is not a boundary, there is no thing that could be the boundary of our hypothetical triple integral, meaning that it's not that these two integrals are different, it's that there is no triple integral to talk about, because there is no solid R whose boundaries are given surface. So it's not that this equation is false, it's that this equation makes no sense at all. Everybody see the problem? That means this is meaningless. It's not just wrong, it's meaningless. That's no good. Right? So, and of course all the rest of this is, only garbage follows from garbage. This is a dangerous little landmine, and I increasingly over the years, as I've taught multivariable calculus more and more, I make a more and more emphatic point about this, and the number of students that make this mistake is steadily decreasing. right? But it's still not 0. So anyway, that's my pitch. I hope y'all will be very, very careful about this in any application of the divergence theorem. And by the way, likewise, Green's theorem. Right? Green's theorem is for boundary circulations. If you just have a regular line integral, if it's not a boundary, it's not a circulation, and there is no Green's theorem. So heads up on that one as well. Same deal, different dimension. Okay. All right, speech over. But you know what? Maybe I will go ahead and pause. Does anyone have any questions about this, clarifications? I feel like you understand where the landmine is and how not to step on it. And by the way, how would you solve a question like this is a topic for another time. The fact that divergence is 0 does lead you to something really useful called surface independence, and we'll talk about that again late, either Friday or Monday. But topic for another time. Okay. All right, so a little bit of physics, but y'all have heard me say several times this is not a physics class, and I don't feel obligated to be thorough in discussions of physics. But I do think it's pretty cool that Gauss's divergence theorem really is super useful in a lot of physics scenarios. So I think it's worth showing you some of those scenarios. The other thing is kind of the opposite in some sense. The physical scenarios that I'm going to show you are wonderful physical metaphors that you can use as tools for your imagination as you're trying to understand, as you're trying to develop some sense of intuition about how the divergence theorem works itself. Right? And so don't think of this as math is going to help us understand light bulbs. Think of this as light bulbs are going to help us understand math. And I think it's really nice in that sense. That's my primary motivation, honestly. All right, so here we go. Let's suppose we have a light bulb. Here it is. Right there in the middle, this is an LED light bulb. A teeny tiny little point light source, call it. Not exactly, but close. Teeny tiny little source, and then a whole bunch of air taking up the rest of the bulb, or vacuum, or the point is not light bulb. Okay. All right, and what the light bulb, of course, does is it generates photons which flow, and they basically flow like a fluid. And here's how this particular fluid is flowing. It flows kind of outward, radially outward. Something like that. And now something to point out about this picture I've drawn. Photons always move at a constant speed, right? Speed of light, famously constant, right? Why didn't these arrows all have the same magnitude, you might ask? That's a very good question. So I want you to recall there are two different ways that we can use a vector field to represent a fluid. One is to let the vector field be the velocity. And recall then, if vector field is velocity, then flux tells you volume of fluid per unit time. Which, as it's going to turn out, is just not what we're interested in this case. But remember, there is a second way that you can use a vector field to represent a fluid, and that is density times velocity. So, and that's what I'm using here. This vector field, let's see here, I'll write it here like this. The vector field is density times velocity. When you use this to represent the flow of a fluid, then flux no longer tells you volume per unit time. Flux tells you quantity per unit time. If you're talking about mass per unit volume as your density, then you get literally the mass of fluid per unit time. Here, I'm thinking of this as more of a population density, number of photons per unit volume. And so the flux that we're going to talk about here, flux is going to tell us the number of photons per unit time passing through a surface. And that's what we're going to be interested in this case. So if you think about it, sure, the photons are all going at a constant velocity, yeah, but the density is lower farther away because the photons have spread out from each other. And so lower density means shorter field vectors, as you see here. Is everybody all right with that? Okay. So now, what is the formula for this vector field that represents the flow of photons? I could write it down. In fact, I have it written down basically on the next page, and we'll talk about that when we get to the next page in a few minutes. But what I want to do is talk about how the divergence works out, and it's a tedious calculation if you do the algebra, but we can actually do it. And here's an example. If you look at a point like this, where I have a little green dot there, the divergence is going to be 0. And that's algebra that you can confirm by brute force if you're so inclined. And it's one of these things that everybody should do it once in their lives. I know I say that a lot, but there are certain calculations that, tedious though they are, don't trust me, right? You should check for yourself, and if you do, you will find that you get 0. Now, let me point out, here's a really cool argument. I can skip all of that algebra by making the following physical argument. And this is one of the things that I love about having physical metaphors for math situations, is the nature of the physical world can kind of tell you what you really expect ought to happen in the math. Right? So here's the argument. Let's think about a little ball here in the vicinity of the point that we're looking at. And looking at that ball, let's ask about, well, how much flux of photons is there through that sphere, the boundary sphere for that little green ball? Well, let's think about how flux works. Flux means that there's little photons, and we want to keep track of how many photons are flying out of this ball. Well, here's a photon that approaches this ball. It comes in like that. Now, this represents negative flux because the photon is going inward, not outward. Okay? So each photon that hits this ball counts as negative flux, except a billionth of a second later, it leaves out the other end, going outward, not inward, thus now counting as positive flux. The number of photons going in, the number of photons going out is always exactly the same because they're literally the same photons. Does that make sense? Yeah.
And are we assuming that the ball is so small that it's the same, that the flow doesn't decrease?
This could be any size ball. I mean, I guess for kind of convenience, I guess it's nice to think of it as being small-ish. But it doesn't. This is true of a ball of any size, a sphere of any size, because no matter how big it is, any photon that goes in goes right back out. So yeah, so this actually holds for no matter how big the ball is. Yeah. Everybody good? So what does that have to do with this calculation here about divergence? Well, keep in mind this little sphere being the boundary of the solid, and I already know that the flux is 0, and I know flux is a triple integral of divergence. What do you think the divergence could be? Right? I mean, especially now, here's where it's nice to think of it as being a small sphere. Right? As this gets smaller and smaller, the divergence is going to be approaching a constant. The flux has to be, though, exactly 0, and that means that the divergence kind of has to be 0. Right? Now, so take your pick. You can either write down the formula for this vector field and compute the divergence, and side note, that has a lot of square roots in your denominator as you're computing the various partials, and it's an ugly calculation. Take you a page and a half. I don't know. Depends on how big you write, I suppose. But it's a fair amount of slog to compute the divergence of this vector field. Or simple little sort of intuition about how this particular flow scenario is, lives in the real world, and it's almost instantaneous to realize divergence kind of has to be 0. So, very valuable intuition for helping you understand the math. Again, the purpose here is not for math to help us understand light bulbs. It's for light bulbs to help us understand math. Is everybody okay with that? Yeah.
So somewhere in between the where photons are created and the surface of the bulb.
Yeah.
Does flux ever become negative? Because
Not in this case. No, that's right. That's just not how photons work. Yeah, photons. Well, okay. In this scenario, as I have it set up, photons. They get created and then they fly off and just travel at the speed of light arbitrarily. Yeah, that's right. Now, I suppose there are some scenarios where maybe you have a bunch of light that hits a dark colored surface and then the photons disappear. Actually, I don't. I think they do disappear because they get converted into heat or something. I don't know. It's been too long. But in this scenario here, there's no negative divergence because no photons are disappearing. Everybody all right? Yeah.
So I guess it'd be somewhat discontinuous in the sense that it's positive only at that point and then anywhere else.
So here's where we have to kind of dial back. I mean, I had previously said this is basically a point light source, but there is no such physical thing, right? There is no such thing as mass that happens at a single point. So I step back from that statement in the context of black holes or something. No comment. I don't know. That's not my area. But yeah. So what I was going to say, I am thinking of this as a little LED, and LEDs they're not points, but they are teeny tiny. And so as long as you're away from the actual light source, then divergence is zero. Yeah, right. Okay, now let's talk about a different little sphere. Let's talk about this little sphere here. Right, teeny tiny little sphere, but this time going around the LED. Okay, let's talk about the flux through this purple sphere. Okay, well, photons that shoot out of the LED count as positive flux as they leave and never return. There is no opposing sort of negative flux when it entered. These photons never entered this purple sphere. They were born inside the purple sphere. They left, end of story. Does that make sense? So through this little sphere here, we're going to have a high flux. There's going to be a lot of positive, large flux through this purple sphere. And now let's ask the question, what is divergence? Well, divergence is flux per unit volume. We have a large flux through a very small volume. And large divided by small is huge. So you would expect, and again, if you write down what the actual vector field here is, then you would find that the divergence is zero everywhere except for where the LED is, and where that is, the divergence is huge. Okay, now, last observation I'm going to make about this before we go on to the next one is just a callback to something I told you all a long time ago. You remember I've tried to persuade you that, for example, that flux, it happens, we measure it on the boundary. So you think of boundary flux as being on the boundary, but I claim that's an illusion. That's not really where the flux happens. The flux happens in the interior. It's an accumulating quantity. It's adding up over the interior, and the boundary is just where we measure it. And I gave you all this comparison to the fundamental theorem of calculus. Let's talk about change. You measure change on the boundary. A, B, the curve goes like this. You measure the change by f of b minus f of a. You measure it on the boundary, but it happens in the middle. It happens where the derivative is large. The density points to where it's actually happening. Now you can see that when you're talking about the fundamental theorem of calculus and change. It's hard to see it when you're talking about divergence, and flux, and three-dimensional. We don't have a graph. There's no graphs anywhere in this picture. It's a lot harder to see. This particular physical scenario, though, I think actually makes my statement extremely believable. let's return to our original scenario. We have this bright bulb in the middle, and let's see here. I'm going to use blue to represent this this sort of the plastic part of the bulb. The sort of the outer thing that protects the little LED in the middle. On that blue sphere, a lot of flux. How many photons pass through this blue surface? All of them, just like the small purple sphere. So, large flux on this blue sphere. And now I ask, where did that come from? Are those photons being created here on the... No nonsense. No, they're coming from the LED. Of course, that's a light bulb. That's how light bulbs. LED is the thing that's making the photons. The LED is what's making what becomes the flux out there. The LED, the place where the divergence is huge, is where the flux is actually coming from. Right? The flux that we see on this blue surface, it's not coming from the blue surface. It's not coming from this green point right here. Divergence is 0 there. There's no photons are being created there. Right? 0, divergence being 0 is our algebraic indicator that there is 0 flux happening at that point. Divergence being huge on the LED itself is our indication that is where the flux is coming from. So, wonderful example of again, a physical metaphor for the mathematical ideas that I've been trying to push on y'all. I think that's nice. I like this example for that reason. All right. Okay, here's another example that I have 2.5 minutes to do. I'm going to be really quick with this one. I just want to point out that there are different kinds of fluid. The details of this particular example are really not that important, but I do want to point out that there are different kinds of fluids. Photons are created, right? And yet the density of photons isn't changing. If you look at, how many photons per cubic inch are there in this general vicinity, whatever, it is what it is, but it's not changing. We're not collecting photons. The photons just fly through and keep flying through. So any given instant, the number of photons per unit volume it doesn't change. It's always the same at any given point. So other kinds of fluids don't behave that way. And this example here, I'm imagining I've got a large balloon, something like this, and that my balloon is expanding like this. I don't know, maybe somebody's got a heat source in there and the balloon is getting larger or something like that. Right? As the balloon expands, all the air on the inside kind of has to expand along with it, thus giving you a vector field that looks kind of like this. And so again, I have an outward flow of fluids, but notice nothing's being generated. Right? The amount of air inside of this balloon is the same air. It just got heated up. It's just expanding. There's no new air. Nothing's being created. But the density is not constant. Right? As the balloon expands, as it heats up and expands further and further, same number of air molecules. Bigger volume means a lower density. Right? So very different kind of a fluid than the photon fluid. And the divergence theorem, and here's the divergence theorem applied to this scenario, and I'm going to just wave my hands and assert that the flow of the air is kind of like this, and you can compute the divergence of that. The divergence ends up being 3K, good exercise. Take this vector field, write it in coordinates. Take the divergence using the formula, which is in terms of the coordinates. You'll find that you get 3K. Make sure you can get that. If you can't, come to office hours, we'll talk about it But make sure you get 3K as the divergence for this vector field. So what does this 3K mean? Is this pointing to where air is being created? No, it's a different physical scenario. This 3K is representing how as air flows outward, the density in a given vicinity is decreasing. I had a certain amount of air in a given region. As a bunch of it flowed out of there, now I have less air in there, and this is pointing to how that density is decreasing. Okay, and that's all I really need to say about this example. All right, y'all have a good one. We'll draw the line right here, picking up here on Friday. Have a good day. See ya.